Hello, this is Jason Kendall. Welcome to the next of my introductory astronomy lectures. Today we're going to be talking about the cosmic microwave background. Last time we were talking about the nature of homogeneity and isotropy. Then we talked about the nature of the hot Big Bang and how it relates to redshift. Now we're going to look at observational evidence, one of the most amazing and compelling pieces of observational evidence that shows us that the Big Bang actually occurred, and it's the cosmic microwave background. The cosmic microwave background is part of one of the three main pillars of the Big Bang. The Big Bang itself is, of course, a physical model that explains the evidence that we see in the sky that relates to the nature of the universe. So the Big Bang itself has three major pieces of observational evidence, and we are going through them all. Actually, we've already gone through the expansion of the universe. We've talked about the Hubble law. We've seen actually how it works, where it comes from, and exactly how the Hubble law then extends because of cosmic density parameters, the energy density throughout the cosmos. Now we have two left to do, and this is the first of the second left to do, which is the cosmic microwave background radiation, which is the relic radiation from the early hot dense phases of the Big Bang. So what we have then is a key prediction of the Big Bang. The basics of the microwave background are, and let's just say, I'm going to summarize all five here. The spectrum that we see in any direction in the sky is almost a perfect black body. And the temperature of that black body is 2.725 plus or minus 0.0101 Kelvin. So 1 millikelvin is how well we know the black body. The temperature is measured is nearly perfectly isotropic. Nearly perfectly. Nearly is important. There's a big dipole anisotropy due to the net motion of all of the sun and Earth through the cosmos. And then finally, there are tiny, tiny, tiny anisotropies, differences in the appearance in different direction, but they're so small that they're only 1 part in 100,000 between any 2 points on the sky. So really, the temperature differences are extraordinarily tiny in the sky. All right. The cosmic microwave background is a key prediction of the Big Bang, and so the first law of thermodynamics actually tells us all about it. So first we have to assume that everything is homogeneous and isotropic and so forth and so on, and then we're going to start with the first law of thermodynamics, and these equations tell us and give us the story of how the cosmic microwave background is a key prediction. So the first law of thermodynamics shows dq equals dE plus pdV, which means a small change in the total heat content of a system is equal to the energy input, meaning some sort of energy input by any form of energy input. And then you add to that, given the pressure on the system, if you change its volume. So what we have is that you have the change in heat is equal to the change in internal energy plus the pressure times the change in the volume of the system. And that comes from, the thermodynamics comes from the studies in the 19th century to understand heat engines. But the box that we're talking about and the system we're talking about is the universe. So we shouldn't expect there to be they shouldn't expect to be heat flow into or out of the universe. All right, that kind of makes sense. With no heat flow into or out of the universe, the dq, Dairy Queen, whatever, no, not Dairy Queen, small change in the heat content is 0. So we should expect that to be the case. Now the third equation, P sub lambda, is the energy density due to light or highly energetic particles such as neutrinos. So radiation based upper relativistic particles, and that includes light. And so the radiation pressure is related to the temperature to the 4th power, and that alpha and the 1/3 are just scaling powers that relate the pressure to the temperature of the 4th power, which is very interesting, that radiation provides pressure according to its temperature. Yeah, okay, well, it's just an energy density. The pressure due to radiation is very small when the temperature is low, but as the temperature increases, you can have a larger and larger energy radiation pressure. All right, and the energy density that then we care about then is proportional to the if you have a perfectly homogeneous spectrum, absolutely perfectly homogeneous, then the energy density, then the pressure density is proportional to one is equal to 1/3 of the energy density. All right, that's fine. So the pressure density equals 1/3 of the energy density. So we can then say, there's the energy density now is equal to alpha T to the fourth times the volume of the universe. So the radiation pressure is equivalent, well, I'm sorry, the P is not radiation density, it's pressure. Radiation pressure is proportional to temperature to the fourth power. But the pressure is an energy density. And so the energy density, the pressure due to the energy density of light is equal to 1/3 times that power. So then we know that if we have the energy of light, the energy density is the 8 T to the fourth divided by the volume. Then we have energy divided by the volume equals an energy density, and that's alpha T to the fourth. Okay. So now we do know that the volume of the universe scales like the scale factor to the cube power. That's fine. I mean, it's got to be something like that. So it's not like there's 17 spatial dimensions. There's only 3. So the volume of the universe scales like the scale factor to the third power. So we plug that in and we find that the temperature is proportional to the inverse of the scale factor. So we actually plug and chug these things together. We use the fact that the energy density, we have a relationship between the pressure and the temperature, the energy and the temperature, which is also related to the volume. We take the pressure and energy equations, take little tiny changes to them, which make little tiny changes to both the volume and to the temperature, and that gives us a change in energy and a change in volume at a constant pressure, and that just involves some elementary calculus. And then out falls the temperature as a function of time, and the temperature then goes as the inverse of the scale factor, which is the redshift. So by taking a small shift in the energy, you get a small shift in the temperature, small shift in the volume, or a small shift in the pressure gives you a small shift in the temperature as well. But really, we're talking a small shift in energy and small shift in volume and small shift in temperature. So all of those things combined together give us the fact that the temperature goes as the redshift. So therefore, if you look at the temperature today, T sub naught, and this redshift for that time is 0, then the temperature back in time is higher because the redshift is higher. So the temperature will drop as time goes on. And that's what a key prediction of the Big Bang is. Using relatively simple physics, the first law of thermodynamics, the known radiation pressure due to a thermal blackbody spectrum, the known energy density of a blackbody spectrum, and the fact that the universe is expanding according to the scale factor. And we can use 19th century physics in order to make this prediction. In fact, this prediction came about in the 1930s that this should be occurring, actually 1930s and 1940s, as people were doing studies of nuclear bombs and so forth. So this is an old prediction that if you have an expanding universe and it's described by a redshift, then we should see a temperature rise as we go in the past. And this is why we think that the temperature was hotter in the past, because the size of the universe was smaller, the total amount of energy, heat in the universe stayed the same. The total amount of heat, that's a kind of interesting way of talking about it, the total amount of heat is the same, but yet how it's allocated between internal energy and the volume and the pressure changes. All right, so we then assumed, remember we assumed the entire thing was based upon the idea of a thermal blackbody. So the pressure, the pressure due to a thermal blackbody radiation was given previously, and the energy density was also framed in terms of a thermal blackbody. So therefore, if today we see that the current temperature was 2.725, we can still run it backwards in time. Now, there's a reason why we would even think that we could actually predict in a very scary way what the current temperature should be in order to see what it is today. This is really something. We can actually make a prediction. We'll talk about that when we get to nucleosynthesis. But first, let's look at the nature of black body radiation itself. And again, all black body spectra are completely identical. They only differ by the temperature. That's the only thing. So this shape, if you see it, you've got a black body. And all stars have black body radiation. They're relatively so because they're hot, dense, opaque objects. Opaque means that the energy gets bounced around inside of there and thermalizes the entire star. Now that's interesting to say that the cosmic microwave background is a black body because at some point the energy has to bounce around in such a way that it all becomes the same temperature. However, you and I know that looking around in the stars today that the universe currently has multiple different temperatures. In the summertime it's hotter, in the wintertime it's cooler, the equator is hotter than there, and the surface of the sun is hotter, and so there's all sorts of different temperatures all across the cosmos. But yet we're describing the background radiation with one spectrum. So here's the effect of the expansion on the cosmic microwave background. Today it's seen in the radio as a black body. That's kind of letting the cat out of the bag. But if we go back and back and back and back in time until the universe was only 1 second old, the universe was mostly gamma rays. So if it was gamma rays when the universe was 1 second old, at about 100,000 years, it would be invisible light. In about 10 million years, it would go down to infrared, and today it's in the radio. So if you were around when the universe was only 100,000 years old, it would be glowing. The entire universe would be brightly glowing as though it's the surface of the sun. That would be crazy. Okay, so today, though, it's about 3 degrees Kelvin. And that corresponds to a region in the microwave spectrum of approximately 100 gigahertz, which is about a centimeter or so wavelength, and that is longer than infrared. So it's much, much longer than visible light. It's much longer than infrared. It's in the microwave region where things are about 3 centimeters longer. So that's where it's peaking in the microwave spectrum. So it was actually one of the most important discoveries ever in the history of everything. Hubble's discovery of the expansion was catastrophically huge. But then it led to a whole bunch of things to say, how do we explain the cosmic expansion? And then this particular discovery even went deeper into the past. So what we find is that you could make a prediction based on this idea that what Hubble found, that the universe had a hot beginning. And the prediction of the cosmic microwave background was given by Alpha, Hermann, and Gamow in 1948 when they were working on Big Bang nucleosynthesis, which we were going to be talking about. And it was pretty much ignored because nobody figured they could ever see it. But then along come a couple of researchers, and were looking with when they were working around, and this got them the Nobel Prize. So Penzias and Wilson got the Nobel Prize for discovering the cosmic microwave background using the microwave receiver that you see there. So how did they do it? In 1965, they were working at Arnold Penzias and Robert Wilson were at Bell Labs in Murray Hill, New Jersey, which is really right close to where I'm at in New York City. And they were mapping the sky at microwave wavelengths, and they were also doing some preliminary tests with the Echo satellite in order for Cold War stuff, so that we can talk to people over in Manchester, England, by bouncing microwave satellite transmissions off of Echo 1 satellite. And so they were doing some tests with that, and part of their tests were mapping the sky at microwave wavelengths. But they noticed that there was a faint microwave background noise. And that background noise was something they couldn't get rid of. And so they were, they're good researchers. So they say, well, we got to find out where the heck this background noise is. And they thought there were a bunch of equipment problems. They replaced their amplifiers because, who wants that static? So they must have bad amplifiers. They must have bad things in their radio amplifiers. Well, they replaced that and still was there. They went up into the antenna feeling desperate and found that there were some pigeons that had roosted, and they cleaned out the pigeon poop from the antenna because it's a big, big, big antenna. And so they cleaned that out, and it was actually part of their research paper is actually said, okay, this was assured that wasn't a problem. They went out and discovered that no matter what they did, changing the amplifiers, cleaning out the pigeon poop, or anything that they could think about, they discovered that it was literally coming from all directions in the sky at once. And what this did is that this gave them the cosmic. This was a discovery that gave them the Nobel Prize, I think in 1978. So I think I got the wrong number there, but they discovered by accident the cosmic microwave background radiation. Now the funny part is that up the hill and up the street in Princeton, New Jersey, there was another team member led by Peebles and Dickey that were building a similar instrument in order to purposefully go and look for the cosmic microwave background. And they were just about to turn on their machine in about 2 weeks. And then Penzias and Wilson basically called them up and said, "Hey, I've heard that there's a cosmic microwave background thing going on. Could you tell us more? Because we got this background hiss that we think is coming from everywhere." And Peebles and Dickey said, "We just got beat with a Nobel Prize by 2 weeks. Grr, snap, snarl." So they both released a couple of papers. Penzias and Wilson released their paper on the detection, and Peebles and Dickey released a paper on the theoretical background. They had hoped to do the paper on the detection as well, but they did not. So Penzias and Wilson won the Nobel Prize. Well, the universe, therefore, as a result of this, because this glow is happening all over the sky, is filled completely with this cosmic microwave background radiation. It's just light. It's light in microwave wavelengths. And it's almost, but not quite perfectly uniform in all directions. Now, for Peebles and Dickey, they thought it was completely uniform in all directions. And this was the first evidence. Dickey and for Penzias and Wilson, this is the absolute first reference of the proof that there was a hot Big Bang that was predicted, and they found it. They found the predicted radiation that should be there if the universe had a birthday and went through a hot, 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 dense phase, just like we described at the beginning. So now, this glow that is there, that is from the Big Bang, shows a specific pattern that would be equal to if you had random hot gas blown up to the size of the universe. They're tiny, tiny, tiny anisotropies or irregularities or differences in temperature between one direction and another, and some of them are on some of them are one size scale and some are on others. And what you do is you find that they actually match what you would expect if you have tiny thermalized fluctuation if you expanded the size of the observable space to what we see today. Now, therefore, this background radiation, they really studied it hard, cannot be due to background point sources. It can't be, because there are too many other things that it's too smooth on too small a size scale for it to be due to that. That would imply extraordinarily tiny, extraordinarily close, extraordinarily dense objects, so it cannot be background point sources. And it is completely the same temperature down to 1 part in 100,000. But the next trick is it really blackbody radiation? And Penzias and Wilson determined that it fit a cosmic background radiation of such and such a temperature, but they weren't exactly certain that it did have that exact thing. So there is a very specific prediction, as we described before, using simple thermodynamics and simple energy conservation equations, and then the expansion of the universe as known by everyone. There's a prediction that it should be a perfect blackbody, that it should be characterized by a single temperature. But now there was a tantalizing thing that Penzias and Wilson had found, but nobody had the instrumentation in order to do it. So basically, people had to run to the South Pole or go way up high in altitude or get out in orbit to actually determine conclusively whether or not this is actually a blackbody radiation. And that was one of the main key hunts that was on in the 1970s and 1980s in order to determine whether or not this truly was. And finally, an incredibly important, well, there's some other data you can go check out and see all the microwave data, the missions that were done in order to actually found that, to detect it. So one of the most important missions to discover whether or not it's actually a background radiation was done and released in 1992. And this is the Cosmic Background Explorer satellite, which was a NASA mission to go and actually map the cosmic microwave background. So the COBE satellite, Cosmic Background Explorer satellite, was the first satellite that would be capable of detecting whether or not it truly is a blackbody radiation. And in 1994, they published this result from the Far Infrared Absolute Spectrophotometer, which was one of the instruments on board COBE as it orbit a spacecraft. And they found that it was a perfect black body to within 2/10 of 1%. And the temperature they found was that it was 2.725 Kelvin, or almost 2¾ degrees above absolute zero. And normally when you report data, you always say what you expect your error bars are and how well you know it. This data is so incredibly good that they had to use 400 sigma error bars. The standard 3 sigma error bars would be too tiny to actually see. And so when this was published and presented at the American Astronomical Society, there was a long-standing ovation for it, because this finally was proof that the cosmic microwave background was a true black body as averaged over the entire sky. So even averaged over the entire sky that they took, it still is a perfect black body to 99.99999%. That's what 400 sigma is. It's even more than that. But basically, we really know that there's a cosmic background radiation, and it's really a black body, and it's really in every direction, and it really permeates every location in the universe. All right. So the cosmic background DMR, so then there's a second, the differential microwave radiometer, looked for anisotropies in the cosmic microwave background. And so what it did is it looked for temperature differences across the sky. And it mapped things. It said, okay, fine, the FIRES is going to go look for specific whether or not it's actually a black body and take a high resolution spectrophotometry at multiple wavelengths in order to determine it. The purpose of the DMR was just to say choose a few wavelength bands, and specifically this was in 53 gigahertz, like 6 millimeter wavelength. And so then you look at those things and look at the temperature differences that you measure across the sky. And so at first, he said, well, what's the base background? And they said, fine, across the entire background, what is an average of 2.275? So this is an early quote, this picture, and so I'm not going to change their early pictures. This call comes from the NASA website, from an early data release. The second picture, or middle one, shows the dipole emission, meaning that is because of the motion of the Sun and Earth and Milky Way through the cosmos. The total sum of all of the motions of the Earth and Sun and Milky Way through the entire universe is reflected in the middle graph. And so where it's hot, meaning red, that's where we're going in the sky, and where it's blue is where we're going away from. And so these are all sky maps. So when you remove the dipole anisotropy, you then get the remnant anisotropies, or little tiny lumps on the size scales of about 7 degrees in the sky. So that's all they could really do, is about 7 degrees. And so they found enormous anisotropies, and most of those were due to the Milky Way. But there was some tantalizing things about the nature of the Cosmic Background Explorer, and looking and saying, well, there's galaxy clusters. We're seeing all this huge thing. So once we get rid of the cosmic background radiation, we get rid of the foreground radiation. The anisotropies are on the order of only a few microkelvins. So this is a very, very, very important result. All right. So then in 1992, the data was published in terms of their better, more cleaner data to demonstrate after removing the top one is the anisotropy due to the dipole. The middle is leaving the Milky Way emission in, and the bottom one is after the Milky Way's contribution has been removed. And those are the fundamental background anisotropies that were discovered by the Cosmic Background Explorer. And what that shows is that this then becomes the new holy grail, is to discover all of these kinds of anisotropies, because the shape and statistics of the anisotropies in the bottom thing is the thing that shows you the print of exactly what happened in the early universe, as the cosmic microwave background was being formed. So now we know not just that the universe is permeated with this light, but now we can use this light to actually probe the deepest, the earliest times in the cosmos in order to understand what was going on back then. So what was then later done is that the Wilkinson microwave anisotropy probe was launched, and it had much better resolution. It was able to determine a much greater depth of the cosmic microwave background. It observed in many frequencies, and then was able to make a more higher resolution map of the sky, and give much better statistics in terms of the cosmic microwave background. Then the Planck mission from the European Space Agency was then launched and superseded and added to the mix. So there are three main missions that occurred in the past that looked for the cosmic microwave background from orbit, with the Planck mission being the most recent. And so these things all came with the same result, that there is a uniform background radiation, that there's small anisotropies, there's a dipole anisotropy, and the first results for this were announced as recent as 2013. So here's what Planck does. This is what they all did when they mapped the sky, and so I'm going to kind of show you how the mapping occurs of the cosmic microwave background to show it to you. Now, the only thing that's really kind of deceptive about this video that European Space Agency put out is that it makes it look like that the little critter is making a beam, like Cyclops in the X-Men or something like that. But no, it's not painting a picture. It is looking to see what is out there, and the beam, rather than coming from the spacecraft, that's the beam that it's looking along. So the light is coming from the thing that's being painted and going to the spacecraft. So it's what is finally being observed. And so it's not being painted, it's being observed. And so then when we spread it out to show a full sky map, we then compare it to the optical image of the full Milky Way, and that's the Planck map that was released. And now we can see that this is what the little spacecraft does. It actually observes in radio frequencies or microwave frequencies. So the three spacecraft show roughly the same results. They all show a tiny variations in the cosmic microwave background. There is increasing resolution of the anisotropies, with the Planck being the most, highest resolution, COBE being the lowest. All of them provide incredibly important data because these are the three main missions that have done it. And they contributed massively, and without exception are some of the most important missions to have ever flown in terms of understanding fundamental science. So what does this cosmic microwave background really look like, and how do we get it? So from the Planck mission, again, we have, first you take the full sky map that was created, map out the individual sources in the sky, and then remove them or subtract them from that data. And then you make a map of the radio emission due to the Milky Way galaxy itself, and then you subtract that from the data. Finally, you look at dust emission from the dusty clouds that float around in the Milky Way, and subtract that from the data. And once you're done with that subtraction, you're left with the cosmic microwave background. And that is what is in the sky when you finally take into account the contributions from the Milky Way and individual point sources, and spend a lot of time deciding which is what and what is which. And so those all-sky images are provided by the European Space Agency. All right. So we can actually say that these three probes provide spectacular confirmation by amazing observational work by three different groups, two different space agencies, and show that there's a strong case for the Big Bang, meaning there was a perfect blackbody spectrum which was predicted in the 1940s. It's characterized by a single temperature across the sky at 2.725 plus or minus 2 millikelvin. It fills the universe uniformly, and the tiniest structures are only at the 1 part in 10 to the 5th. So those lumps and bumps that we saw in that final thing are only tiny bumps that are differences in temperature of 1 part in 100,000. It's not like something is like 10 degrees hotter or 100 degrees hotter. No, it's 1% of 1,000th of a degree. 1% of 1/1000th of a degree, or 1%, 10% of 1% of 1% of a degree. So it's a really, really, really tiny, small amount of temperature difference that's found. And it's that tiny temperature difference and those statistics on that that lead us to understand what happened in the early cosmos. And that's what we're going to talk about right now. So if we go back in time, all the way back in time to when it's hotter, let's go back in time until the universe was so hot that it was as though that the universe was ionized, where there were no atoms, where atoms were not possible to have. Because if the universe was so hot that there were no atoms, then the electrons would be free, and if the electrons are free, they're zipping around, and electrons interact very strongly with photons. And so they can scatter and absorb and re-emit with great ease. So if the electrons are free, they'll scatter with the photons, and the electrons pull on the protons. So basically, the electrons and photons will become all of the same temperature. What temperature does that happen? Roughly about when the average surface temperature as of an M dwarf star, or about 3,000 Kelvin. To get to 3,000 Kelvin, when the current temperature is about 2.75, we have to go back to a redshift of 1,100. So at redshift of 1,100, the entire universe was ionized and glowed like the surface of a star, as though we were in the surface of a star. That was the universe at redshift 1100. So what was it like in that time when the universe was at 3,000 Kelvin? It was too hot for atoms to exist. They hadn't formed yet. So we're going back in time, so we're actually running the clock backwards. So we have some point, so we're close to time zero. We don't know yet how far that is. I haven't described it. But sometime after time zero, it was still far too hot for atoms to have formed. But there were a lot of photons, they had a lot of high energy, and they kept the protons and electrons from combining into atoms. So therefore, everybody was scattering around. And so in this little diagram, I'm going to play a game here, and the yellow squiggles are photons. They are particles of light. The red dots are protons, and protons are the heavy little things that make up the centers of hydrogen atoms. And then the electrons will be the blue dots with the yellow shell. And I use a yellow shell because electrons really do a good job of scattering off of photons. All right, so first and foremost, let's see what the universe kind of looked like at that time, how things moved around. This comes from NASA Jet Propulsion Laboratories as they described their contribution to the ESA platform. And so what we see here is we have little green dots. The little green dots are the electrons, the big red dots are the protons, and the little bouncy doodle whackers, those are particles of light called photons. And so the photons would bounce off the electrons and scatter off of them, and so therefore they would impart energy to each other, and they would scatter, 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 and so because they're all billiard balling around off of each other, they all work out to become the same temperature. And because they're the same temperature, because they're interacting so rapidly and the electrons and photons are interacting so much, they stay at the same temperature. And because the electrons pull on the protons really hard because of the electrostatic force, then the protons get to be the same temperature as the electrons as well. So this is what we call Thomson scattering, and it's the scattering of photons off of electrons. All right. Now then, here's a picture of what it means for a scattering event to occur. So we got this hydrogen atom sitting there. Maybe it got cool enough so that, I got close. So the electron got close enough to make an atom. And along comes an energetic enough photon. And here comes the photon, comes along, boom, and the electron ionizes, it absorbs the energy of the photon, it ionizes, and now it's no longer part of an atom. There is extra energy, then it provides a little bit of a kick, so the electron moves off into another direction carrying that energy. But, another ionized electron then will come along, and boom, it will be absorbed into the atom as an atom and then emit the photon, and boom, the photon will then move off onto its own way and going, and it'll scoot, scoot, scoot over here and over there and over here, over there, and then boom, the electron and photon can scatter off of each other also. So they interact like a bouncing pair of billiard balls, and off they go, and the electron then comes back, they pull on each other, and boom, they try to create a hydrogen atom. So this process that we see happened over and over and over right around the time that the cosmic microwave background was being formed. And so the light that was there was scattering off of these electrons, and it was as the universe was cooling. Now I've put a background grid to show that the universe is expanding, and so let the universe expand. It's always been expanding, but now the universe has expanded enough that it's made the light too long a wavelength. Now that the light is too long a wavelength, it can no longer ionize the atoms, and so therefore the light doesn't interact anymore. This is called the epoch of last scattering. And it's the last time the photons had scattered off of an electron. Because now the electrons are in atoms, so they can't scatter anymore. So there were two processes, ionization and scattering. So there was a combination epoch where all of a sudden, or it's called recombination, which is really irritating, but it's a combination epoch where where things start to become atoms. They go from free to becoming atoms. So I was kind of doing two epochs at once, the combination, recombination epoch, and the last scattering epoch all at the same time. And so there was a time when nothing was making atoms, and they were just scattering only. And then it got cool enough so that atoms could start to form, but there were some photons that were wandering around that could ionize a few. Eventually, there weren't enough of those, and then there were still some free electrons that could scatter a little bit, but then the universe stretched and didn't have enough energy to keep the electrons ionized, and so then there became atoms, and now the photons streamed freely, and it's now these red photons that you see kind of zooming off to the lower left that is the cosmic microwave background. So that's really something. So there were three basic epochs of the cosmic microwave background. Right around redshift 3570, or when the universe was about 50,000 years old, the average temperature of the cosmos was about 10,000 Kelvin, or just under 10,000 Kelvin. Everything was completely ionized. There were absolutely no atoms whatsoever. They did not exist. However, there were nuclei of atoms, and there were electrons, and there were photons, and it was hot enough that they were all in the same temperature. So at the era of radiation matter equality, prior to this, radiation had the highest energy density, but after this, matter had the highest energy density, and this became quite apparent very soon. So recombination, which is kind of funny because it wasn't like they were ever combined to begin with, and that's a really irritating logism. It should just be combination, but it's not. Thanks, guys, for historical stuff. We call it recombination. That's silly, but whatever. The epoch of combination happened at a redshift of about 1370. The universe had expanded and cooled to a temperature of about 3700 Kelvin, and that was when the universe was 250,000 years old. And decoupling occurred when the electrons and photons no longer were in thermal equilibrium. That's what decoupling means. And so when they're no longer in thermal equilibrium, there's still some scattering events, but now the electrons are no longer have the same thermal temperature profile as the photons. And then finally, last scattering is the time at about a redshift of 1100 when the photons last scattered off of some electron. Now, all of these epochs are, of course, not like momentary things. It takes time for them to kind of smear out, and because, there's a lot of electrons, there's a lot of photons, there's a lot of protons, there's a lot of atoms, and so basically the only thing that we can say where it's been traveling in a straight line to us is from the epoch of last scattering. So the last time a photon was scattered, until we observe it, we're seeing the universe as a picture of it was when it was about 360,000 years old, or sometime between 240 and 360,000 years old, if a photon came from one of those regions. So we're looking at the universe as when it was only about 360 or 350,000 years old when we look at the cosmic microwave background, and that is what we see in the sky. That is the last scattering surface, when the photons were finally able to stream freely towards us. So this is the high-resolution image of the last scattering surface when the universe was only about 360,000 years old. And compared to Kobe's very poor resolution at 7 degrees, the angular size of that was able to be seen by Planck is much, 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 much smaller. Luckily, Planck can get down to much tinier angles, and the last scattering surface, if you went back, how big was the universe? You could look at the scale factor. The universe was 1,000 times smaller. And what's 1,000 times smaller on this surface? Well, about 1 degree. So a little patch of sky about 1 degree in size became an entire universe. That's a really scary thought. So every patch of sky that you see here became some whole universe. Patch of sky meaning about 1 degree across, which is really interesting. All right, so what it measured, and this is interesting how Planck actually does its measurements, and the critical measurements of the anisotropies to say, well, how do we know what its anisotropies are, and what is the scale measurements? And I'm going to show you what that is, but I need to show you how it actually does a difference in temperature. And this is what we call a differential temperature measurement. What you're going to do is put 2 circles on the sky. And those circles are the beam of the telescope. And that telescope says, okay, what's the temperature inside this little circle? And then you say, compare that to the temperature of a circle at a given angular distance away in the sky. Then rotate it around and do it for every pair of circles at that angular center. So here's what we look at for a large angular separation. It'll look a little like this. So we have a large angular separation, and we do it over every pair of points in the sky. And then we do small angular separations, and we do it for every point in the sky. And then we do even smaller angular separations, and we do them for every point in the sky. And after we've done every point in the sky, every angular separation from that point in the sky for the beam width at a given frequency, then we make a map. And it's called the power spectrum. The power spectrum is incredibly important because it tells us amazing information about it. So the power spectrum shows how big the temperature fluctuations are at that angular size scale across the entire sky, meaning you take the average of the square of the temperature fluctuations, and you see for 2 degree angular separations, we have this kind of static sort of appearance, but the largest peak of all is centered around about 1 degree, and this is the greatest power of the temperature fluctuations, meaning these are the largest amount of temperature fluctuations inside of about 1 degree. Then we have an important portion that's just about between 1/2 degree and 2/10 of a degree, and that is where we get to learn about dark matter and cold dark matter, and well as normal matter. And finally, way out there, we determine the thickness of the last scattering surface, because the scattering surface will knock out the little tiny angular sizes. Combining all of those together gives us the picture of the statistics of the temperature fluctuations across the entire sky, and that's called the power spectrum of the Planck measurements. All right, so Planck's measurements then said the large angular fluctuations across the entire sky, which I give in my little circle diagram on the left, and medium-sized ones in the middle, and tiny, tiny, tiny ones on the right. So the angular size is the separation between the various circles across the circle. So red to blue diagonally across. Not next to each other, but diagonally across. Just like so look at, not next, but across the circle. So a red to a blue across the circle. And then you say, what's the temperature difference across there? And multiply that temperature difference, take the square of that temperature difference and see where the greatest fluctuations are. And the greatest fluctuations happen at the 1 degree angular size scale. And then you have this strange pattern that occurs across this size scale difference. All right, so what this means is that the universe kind of can be perceived as ringing like a bell, because these are ringing oscillations on the surface of a sphere, and that's another way of looking at it. These are spherical harmonics, and that's how, if you look in the literature and took a cosmology class, you would be talking about the nodes of the oscillations and the vibrations, and you take the statistical version of this, And then they would say, okay, what is the height, the importance of the statistics on various nodes of the vibrations? Okay. So each of these moments, which are the multiple moment, is what they call them. So the dipole is one direction, the other. And so we have moments, meaning sources or points about which the vibrations apparently occur across the sky. The fewer, the more dipolean, or 1 is just pulsing in and out, 2 is ringing up and down, 3 is a 3-pole moment, there's a quadrupole moment where there's 4 points on the sky that things are vibrating around, and then you get larger and larger and larger moments, which tinier and tinier and tinier size scales. So the higher the moment, the higher the pitch, the shorter the wavelength on the spherical surface. The universe could be seen as ringing like acoustical oscillations. And in fact, that's a good way of thinking about it, because remember, the electrons are vibrating, or not really vibrating, but being shoved around by the photons. As they're being shoved around, they're moving. And if they're moving, they're bouncing against the photons, right? So we can actually think of the matter as oscillating back and forth as a result of it. And so the oscillation also applies to the photons. All right. The first peak, the largest peak, is indicative of the universe, the size scale of the universe at the time of last scattering. This is the time when the universe became transparent. And so the size scale of the universe on the sky was about 1 degree. So everything that was 1 degree was the same size as the universe. Take our universe and go back in time. How big was the universe on the sky? It was about 1 degree. So therefore, we're looking out into space. So we're looking back in time at other locations that have expanded away from us since that time. So therefore, we're looking at, for every 1 degree patch, we're looking at a separate universe, a separate one. So we're looking at separate universes, and each of them have about 1 degree. So we now know that there's lots of universes that are very similar to ours way out there, and they all had the same size of last scattering. So the degree of flatness, the peak and the degree of flatness. If the universe was open, the peak moves to the right. If the universe was closed, it moves to the left. And this peak shows the biggest compression or lump at the time of recombination. The whole universe became transparent. So we can predict whether or not the universe is an open or closed universe in terms of geometry by where this peak occurs, left or right. Interesting. And how that works is, if you have light, you can see like how big things appear to be. The patches, if they are flat, if the universe is flat, then the hot spot has its real size. If it's an open universe, the hot spot is actually smaller in apparent size than it actually is, so it moves to the right. If the universe is closed, then the hot spots appear bigger than they actually are, so the peak moves to the left. So this shows the relationship between the power spectrum and the angular size of the hotspots. Okay, so that also measures the total amount of normal matter in the universe. The more normal matter, the higher the peak. And because the normal matter gives lots of ways to cool off and falls in the gravity well. So the more normal matter there is, the higher this peak will be. And this is a comparison of the results from the WMAP that clearly shows that if we map with the universe having a baryonic matter of only about, if we look at the different baryonic matter about 5%, just under 0.046, or about 5%. The 0.546 is about 5% of the entire universe is made up of normal matter. Then that is what we correspond. But if you see that if we alter the total amount of normal matter, we make it more, the peak gets taller. If we make it less, the peak gets shorter. And also see how it kind of bounces the other little peaks to the right. And that tells us something too. So really, if we give it more normal matter, the peak goes up. We give it less matter, the peak goes down. So these are all mathematical predictions. All right, so the next two show a ratio of the height of the next two pairs. The dark matter, the ratio of the height between the two is how much dark matter there is compared to normal matter, which we call baryonic matter. So dark matter doesn't slosh around because it doesn't interact with light, so it doesn't slosh around, it doesn't group, it can't lose energy, so it doesn't really participate in that ringing. And so since it doesn't slosh around as much as normal matter, it basically says is that you will have a greater it shows, so the dark matter, so it increases the difference between them. So the second peak shows how far apart big globs got before they got pulled back together, and the third peak shows the size of how compressed the biggest blobs got when they got smished together. Because, you know, you think about those electrons and protons, they're moving around and they're kind of, on average, behaving like globs that are getting farther apart and closer together. So dark matter weighs all this stuff down, and normal matter kind of acts springy and moves better. So if dark matter, the way to think about it is that normal matter is like a guitar string. If you pluck it outside of the water, it'll vibrate nice and easy. But if you put it underwater, then it will vibrate more slowly. And so it'll change the resonance frequencies between them. So the ratio of these two things is, these two peaks shows you how much dark and normal matter you have. Finally, way out there, there's a tail of stuff that gets damped. And why does it get damped? Because the last scattering surface is not a solid surface. It's not a sharp thing. It takes time for the light to go through the last scattering surface, and the thickness of the last scattering surface, the thicker the last scattering surface is, the more these little lumps and bumps will be smoothed out and become nothing. Actually, there will be fewer and fewer peaks, and it'll just become a smooth curve. So the tiny bumps will get washed out if the transition goes from opaque to transparent. It takes a very long period of time. During the last scattering surface. So that tail actually measures how long the last scattering surface lasted. With all of this information about the power spectrum and doing mathematical modeling of what we know about how matter moves, how the size of the universe works, how energy gets distributed among matter, and how things move around under this course, we can then determine from this data the age of the universe. And the age of the universe from this power spectrum says that the universe is 13.799 billion years old, plus or minus 21 million years. That's really much, the accuracy of that is better known than any fossil in any museum in the world. That is wild. So what's really neat is that we can also determine that we also think, because the shape of that curve also says that at some point deep in the past there was a massive growth. It's consistent with the inflationary epoch interpretation, which we haven't talked about yet, but we'll get to. And that is consistent with it as well. So the main results are, and you don't have to memorize this, please don't memorize this, just look it up. The main result of fitting that curve, there are 6 numbers that are used to fit the curve to the data. See the green curve? The red dots are the data. The green curve is the mathematical model that fits the data. All you need is 6 numbers and the mathematical equations to plug in to fit them. One of the numbers is the Hubble parameter, and they determined it to be 67.31 kilometers per second per megaparsec. Another one is how much dark energy is in the universe. 68.5% of the universe, in terms of its energy density, is dark energy. The next one is baryonic density and cold matter density, and that's the ratio of those two peaks, right? That's about 5 to 1. Is the cold dark matter to baryons about 5.36 to 1. So the total, so of the remaining matter, about of the remaining 21% is cold dark matter and baryonic matter, where only about 5% of the universe is normal matter, baryonic matter. So therefore, we can also plug in the dark energy density, what is the actual energy density, electron volts per cubic centimeter. The baryonic density is given in grams per cubic centimeter, but we don't give dark energy in terms of mass because dark energy has no mass, it just has an energy density. And then we can also plug in a putative age for the universe of 13.799, and that's what we get for this moment. And the link there, the 2 links below show exactly where all these numbers come from. And if we then add one more parameter to it, We now know how much matter is in the cosmos to within 1%. We know how much normal matter is in the universe to within 1.1%. We know how much cold dark matter there is in the universe to 1.4%. And we also know the total amount of dark energy in the universe to 3.7%. This is really strange. That is incredibly strange. And that number is that's a lot of dark energy. And we'll talk about that later. And if you can look at that, that's a very odd thing. It's it's called a core problem with the standard Big Bang model, but we'll talk about that later. Actually, it's a problem with standard particle physics. There are lots of areas of research and things that need to be dealt with, but we're not talking about those. We're talking about the nature of the Big Bang, starting from about 300,000 years after the Big Bang, right? So we're starting from this hot, dense place. And given one more parameter to that model, we get that the total energy density of the universe, which is that omega, what is the total energy density? It is consistent with a flat universe, 0.99995 plus or minus 0.0034, which lets it be a flat universe. It also allows it to be a little bit more dense than flat. It also allows it to be a little less dense than flat. But mostly, it says that it's very consistent with a flat universe. So we actually think that it is a flat universe. So this is the evidence that we have for it. We also have there's also some predictions based on neutrino masses and how many neutrinos there are, and the tensor scalar ratio it determines well. That's best left for you to go look up, because I only have to go 20 minutes in order to understand that. Okay, so as photons propagate through the cosmos from the last scattering surface, we see a wall of photons traveling through the cosmos, and they are illuminating the cosmos as they go. But as the universe progresses in age, matter falls into gravity wells and forms clusters of galaxies. It forms structures like you're seeing created through time. And so it was very, very, very smooth, and then gravity works and pulls stuff together into clusters of galaxies. We now know there's clusters now, but there weren't clusters ago. And as structure is formed, as the universe ages, we go from the left, which is ago, and the light traverses this and gets deflected by the matter in between, so the cosmic microwave background can be redirected by the gravitational field that it experiences as it goes through the different evolutionary stages of the universe as it goes. So the cosmic microwave background may go through things. It might get a little energy here, might get a little less energy there, and so there's a slight shape of the hot and cold spots in the cosmic microwave background. And by studying that, we can actually determine the actual shape of the matter in the universe, and that map looks a lot like this. So undoing the directional data and the lensing that is apparent inside of the data, and taking into account the microwave, what we can't do because of the Milky Way in the way, we find that where it's darker, is less mass, and where it's brighter, there's more mass. So we're looking at huge concentrations of mass that are present throughout the cosmos. And this is the mass through which that the dark matter, this is mostly dark matter that we would be looking at, that the light had to have passed by or through in order to get to us from there. All right, so the real journey that we would have experienced in the cosmos is shown here on this wonderful little video that is given by NASA, and this is called The Journey of Light Through Space and Time. And we can just take a peek at it, and what we find is that this Planck spacecraft busily scanned the sky, and this particular video was created by a NASA group. I think I turned off his sound. I hope I did. Let's see. We got
370,000 years after the universe began.
So I'm going to try to turn off his sound and make it mute, so it'd be me talking rather than somebody else. What we have here is that here's the universe when it was about 370,000 years old, and this I'm dubbing over Charles Lawrence. Sorry, Charles. I'm taking your thunder. So what happened is that the cosmic microwave background, the light is interacting with all the electrons and photons until the universe expands enough so that it's cool that the electrons could bind with the photons, and then all of a sudden they stream freely. Now that was the last scattering surface. So from that point, the photons are scattering. They go through and they pass by galaxies as they're forming in the early cosmos, past the first stars. They get bent in their direction and get redshifted as they travel. Notice the color is changing from blue to yellow. And sometimes they go into a galaxy cluster where they encounter an electron and get a little extra energy hit and get diverted again. They have been redshifted all the way down to the radio light, passing through the entire cosmos until they enter the Milky Way and then get gobbled up happily by the Planck spacecraft. And after this travel that they did, we then map where those photons came from in their 13.8 billion year journey, and that is the map that we see in the sky. So that is what we've seen, and that amazing view. Thank you, JPL and European Space Agency, for creating that video. That was a fantastic video. I'm sure you can go find it elsewhere. And there's some review questions for you to review if you wish to do so. And there is our amazing talk about the nature of Planck and what we know about the age of the universe. The universe is about 13.8 billion years old. We know the expansion rate, and it's all because of the cosmic microwave background. The cosmic microwave background itself is insanely important in order to understand what the history of the universe was. The cosmic microwave background was predicted in the 1940s, observed in the 60s, and it was refined in the 20-aughts and 2010s. So cosmology went from being stories told around a campfire to now a precision science where we know the age of the universe better than we know the age of the dinosaurs. That's amazing.